thank you for the introduction. So this is a joint work with Emanuele Viola. So we'll give you some background of this work, and then we'll talk about some research, and then we'll talk about the proof ideas. So the object we are interested in is pseudorandom generator. So let me first define it. So we say a function that stretches a few input bits, S bits to M bits, is a pseudorandom generator for some family of tests if it epsilon fools every function in this class F. So by epsilon fools, I mean that evaluating on F on this output of the generators on uniform random bits is indistinguishable from F on uniform M bit string. Okay? So if F is a Boolean test, then you're just saying that the expectation of this function is epsilon close to each other. But for this work, we're going to look at non-Boolean tests. So that's why we look at statistical distance. So here, usually we refer to the input length S as the seed length and epsilon as the error of the generator. So the two regime of parameters, you should think of epsilon as epsilon being a constant or epsilon being some 1 over polynomial of n, say 1 over n. So the focus of this work is on this class of tests that's called read-once log space computation. So using a simple probabilistic argument, you can show that PRGs with seed length log n over epsilon exist. And research in pseudorandom randomness is to come up with an efficient construction. Say this P has to be computable in polynomial time or log space. And the motivation comes from the randomizing randomized log space computation. And the assumption on the computation being read-once is because in space-bounded computation, the randomness is assessed in a read-once fashion. Right? So what do we know about PRGs for space-bounded computation? Okay, so for constant error epsilon, and the space is logarithmic in the input length, then we know that from the 90s, we have PRG with seed length that's quadratically far from optimal, log square n. Okay. So what about, say, constant space, right? So it turns out that even now, it's the same, even if the computation only uses 2 bits of space. Okay. The best generator is still log square n. So for this talk, we're going to focus on constant space and some restricted space-bounded computation that is called permutation branching program. So I'm not going to define it here because we're going to look at a different but equivalent model of computation. Okay. All right, so what do we know? So, okay, so for constant error, we actually know optimal PRGs for constant space permutation programs. So actually, this is the same generator that's given by Impagliazzo, Nissan, Richardson, but with a better analysis. So now what if epsilon is 1 over n? So the best generator today is still log square n. Okay. And it's open that to get a subquadratic little o of log square n seed length for even this class is called width-3 permutation programs. So you can think of this computation as using even less than 2 bits of space, say log base 2 of 3 bits of space. And still the best generator up to today is still log square n. So in this work, we're going to look at a different but equivalent model of computation on permutation programs. So the computation is defined by a group and n group elements from the group. So you can think of, so the input is still an n bit string, and you can think of each bit as an instruction. So the way to compute, so the output would be a group element. To compute this group element, you just look at if x1 is 1, then you just multiply g1. If it is 0, then you just multiply identity. Okay, so you do this for every GIs. So for example, if x is all 1 strings, then you're just multiplying g1, g2 through gn. And then you just output the product of all the elements. And if x is all 0 strings, then you're just outputting the identity element in group. Okay. So for example, if you think of G being just the Z2, then actually this is just a small bias distribution. Because if GI can only be 0 and 1, so the 1 coordinates are exactly the parities on these coordinates. Okay. So note that here we are not generating group elements, but the bits xi's. Okay, it's very easy to get confused. In particular, the output distribution may not be uniform over the group. Okay. For example, if you look at the group G being Z3, then here you are just computing a linear sum over mod 3. So the computation is over F3, but the input is 0 and 1. So if G is the permutation group on W elements, then for those of you who know about with W permutation program, they are equivalent. And one direction is easy, and the other direction is that if you look at the transition between two layers, by permuting the vertices on the right, you can assume on input 0, the layer is just identity. And then on 1 is just a permutation on the states on the left-hand side, which is a permutation. So because SW is equivalent to with 3 permutation programs, so the open question that I just mentioned in the previous slide can be stated as the following. So come up with a 1 over n error PRG for this group product over the symmetric group on 3 elements, which is equivalent to the dihedral group on 6 elements with seed length that is less than log square n. And note that this group is exactly the smallest non-abelian group. And the reason to the main focus of this work would be just fooling non-abelian groups. So products over non-abelian groups. So everything makes sense so far? So now I can state our results. So actually we have 3 results. The first one is that we have PRGs. Okay, so first of all, for now, for this software, just assume the group is of constant size. Okay, the focus is on the constant size with bunching program. So we have optimal PRGs for products over groups that are called P groups. And these are just groups of prime power order. So groups with prime power elements. So some non-abelian example would be something that is called the Z2 width product of Z2 and C2, or the quaternion. Okay. So I will define the first one later on. So this optimal seed length was only known for the secret group of prime order orders before. This work by Shahar and Reingold, Trevisan, and Salifatan. So the second result is that we show that we have PRGs for group products over something that's called a Dedekind group with seed length that's optimal when the error is constant. So here, note that I already told you that for constant error, we have optimal PRGs. So here, one thing, okay, so let me talk about what is a Dedekind group. So one definition is that it's just a quaternion, the direct product of quaternion times and Z2 to the T for some T and some abelian group of odd order. An equivalent definition is that a group is Dedekind if every subgroup is normal. So later we will see a third definition that is more interesting. Okay. So previous PRG does not work for unordered products. So this is one feature that how this PRG is different from the other PRGs. And maybe more interestingly, the PRGs I just mentioned is based on the INW generators, and here the construction here is a little bit different. So the third result is that we give a reduction so in that if you can fool group product over secret group, then you actually get a PRG. So if you fool this with seed length S, then you can also fool something that's called read once polynomial over the field FP with seed length that's close to S. So the overhead you have to pay is poly log log n, which is not much. So if you have a near optimal generator for linear test, then you also get an almost nearly optimal generators for read once polynomial. So more generally, this reduction holds for something that's called block products over data groups, but I'm not going to define it. So for this talk, you can just think of this FP polynomials, and the polynomial is read once. So as a corollary, so we get almost optimal generators for read once polynomial over FP for any prime P. So previously, this was only known for F2 read once polynomial, and it wasn't even known for F3. So let me now talk about the techniques behind these results. So the first result actually just more or less follows from this lemma. So you can show that a group product over P groups or with prime power number of elements are actually equivalent to low degree polynomials over FP. So if the group is of constant size, then these are just constant degree polynomials. And this equivalent actually holds even in the read many settings. So read many setting meaning that each variable in this product can appear more than once. So the correspondence would be you think of a group element in a group as a k tuple in fp to the k. So if the group has size p to the k, then you think of it as a tuple. So here the polynomial is in the input xi's, which are bits. So each coordinate will be, in terms of the group product, then each coordinate will be a polynomial, a low degree polynomial in the xi over the field fp. Okay, so now let me give you some examples. So for example, so let me define the width product of Z2 and Z2. So this group has 8 elements, and you can represent them by a triple. So each coordinate is just a bit. So to multiply 2 elements, then if the first element, the last coordinate is 0, then you just do this XOR coordinate wise. And if the last coordinate is 1, then you just swap the XOR on the first 2 elements. So instead of A XOR A prime, you compute A XOR B prime, and you do something similar for the second coordinate. So now I will show you how to simulate this by a polynomial or a quadratic polynomial. So what you really have to do is really just have to keep track of whether the last coordinate is 1 or not, right? So specifically, you just keep track of the parity on the sum of the z, the last coordinate. Okay. So once you know the parity of z, then you know exactly whether you're multiplying the first element or the second element. Okay. So you just do the following. So if the parity here is 1, then you just multiply. And if xi is 1, then you just add xi. And now you check if the parity of z is 0. If in that case, then you just add the corresponding di's. So you can see that this is a quadratic polynomial. So this is for the first coordinate, the second coordinate is the same, and the last coordinate is just a parity. So all of them can be computed by a quadratic polynomial. So once you have this lemma, so this lemma actually was known in the 90s, but it wasn't very explicit. But the proof is not very difficult. Okay. So given this lemma, then if for P groups, for 2 groups which are groups of size 2 to the t for some t, then the group product is just F2 polynomials of constant degree. So we already know that no generators that are optimal for F2 low degree polynomials. So you can use that. And in this case, actually, it fools even non-grid ones products because they are just polynomials. So if P is greater than 2, then it gets a little bit trickier because we want to generate bits, not group elements. So we cannot just plug in generators for F3 polynomials to do that. So what we're going to do is to apply the result by Fox and Kelly and Rigo, Stankin, and Fadan, and a follow-up work by myself and some others. So what this work shows that is the following. So for every constant eta, you can think of this as a noise parameter, you can fool a product over such group with a small bias distribution where the bias is polynomial. Whenever the noise rate is constant and the group is of constant size, plus this noise. So you sample from a small bias distribution, and then now for each output bit of the distribution, you flip it with some constant probability independently. So sampling D requires log n bits, which is good, but then it's very costly to sample this product distribution. So the goal of this work is to de-randomize the noise distribution. So how do we do that? So the observation, so this observation was actually known in 2009 by a work by Lovett et al. And also I think Mecca and David also had a similar observation. So the observation is that if you take a uniform element from Fp, and if you compute u to the p minus 1, then the output distribution is a bit, but it's a bias bit. So it's 1 over p bias. So the lemma shows that a group product is just a low degree polynomial. So in particular, if you compose P with this monomial, then the output, then this is still a low degree polynomial over Fp. So now I can just use my PRGs for low degree polynomial to, and then for each coordinate, I just turn it into a bias bit. Now the overall computation is still a low degree polynomial. So this is the correct that just follows from the pseudorandomness for a low degree polynomial. So now let me move on to fooling this Dedekind group. So the technique is very different, which I think is quite interesting. So first of all, I will tell you something about representation theory, very little, but not much. So a representation of a group is really just a unitary matrix encoding of the group elements. And this encoding is homomorphic, so rho of G times H is the same as rho of G times rho of H. So among all the representations, the interesting ones are something that's called the IRAP, which are irreducible representation. So it's irreducible if it has no non-trivial invariant subspace under any group action by the elements in G. So one useful fact is that if you want to fool a group product, then it suffices to fool all the IRAPs of the group. So because of that, you can just target every individual IRAP of the group and then fool each of them. So just to give you why, so an analog of this fact is that over Zm, then the closest between two distribution over Zm, if these two random variables are close, then this is equivalent to showing that the character, which is a distribution over the unit circle, are also close to each other for all characters. So a generalization of this fact is that for general groups, if two distribution over the groups are close, then actually the IRAPs are also close in expectation. Okay. So you can think of for abelian group, these are just one-dimensional representation. So let me now, because I told you the definition of dedekind group. So this is the first one. And the second one is that it's dedekind if every subgroup of G is normal. So it turns out that there's a third definition that is in terms of the representative, the erap of the group. So group G is dedekind if for every non-identity group element and every erap of the group, the matrix row of G has no eigenvalue 1. So note that row of G is a unitary matrix, so all the eigenvalues are on the unit circle. Okay. What does that mean? That means that if you look at just a single coordinate and you look at row or to the UI, then with half probability it's going to be the identity, and with the other probability it's going to be this matrix. So the eigenvalue, the top eigenvalue is going to be the average of 1 and some other point in the unit on the unit circle. So this average must lie inside the unit circle. Right? So in particular, the operator norm or the special norm is going to be straightly bounded away from 1 when the group is of constant size. So now if you have many non-identity in the product, then this operator norm of the product of eraps is going to decay exponentially in the number of group elements, non-identity elements. Okay. So if there are less than log 1 over epsilon non-identity, then we can just fool this with small, like limited independence, AKY independence, because the test only look at a few coordinates. So let's focus on the case where there are many non-identity elements in the group product. So because of this exponential decay, if there are this many non-identity, then the expectation of this norm is going to be very small, say epsilon to the 100, where this 100 is going to depend on the C here. So all we have to do is to come up with a distribution, pseudo-random distributions, such that the expectation of this product under this distribution is also small. So this is our goal. Now, the idea is to just to feed uniform bits on roughly log 1 for epsilon coordinates. Okay. So if you can do that, then you still have this exponential decay. So this operator norm is going to be at most epsilon. But the challenge here is that you don't know where these coordinates are. And you don't know how many of them. So the idea is to first you guess how many of them by applying log n random restrictions, each one keeping each variable alive with probability 2 to the minus I. So for the right I, then you know that exactly roughly log 1 over epsilon of them is going to be alive. So to save randomness, we are going to use the same randomness for separating these restrictions. Okay. So once you guess the correct number of non-identity, then you just hash these alive coordinates to roughly the same number of bins, and then for each bin you just apply the same uniform bits. So the seed length, if you do the math, then it's not hard to see that this is the seed length, and the analysis is exactly what I just said. Right? So if you have some restriction, it's going to keep exactly roughly this many non-identity elements alive, and then most of this variable, if you hash them into log 1 over epsilon bins, most of them will lie in distinct bins, so you will have independence across the bins, and so you have this exponential decay. So I won't have time to talk about this idea, this result on Ritz polynomial. So let me just mention one idea. So really the one idea is so previous work showed that if you have many monomials, then the expectation of this polynomial has very small bias. So what they do is you just apply a very aggressive random restriction, so keep each variable alive with exponentially small probability. And they show that this is the restricted polynomial is going to be a small low degree polynomial, and then they just apply PRGs for low degree polynomial. And the problem is that there's no bit PRG for F3 polynomials. So this work, we just do the calculation more carefully and show that actually instead, you can show that you can restrict the polynomial so that it becomes a linear function. So let me skip this. Okay. So some open problem. So basically, this work doesn't give you any little o of log square and seed length PRGs except for the P groups. So one interesting question is to improve to get little of log square and PRGs for maybe the Dedekind group or non-abelian groups of composite order, say direct products of P groups and Q groups where P and Q are different primes. And perhaps the most important question is to get the PRGs for S3. Okay, that's it. Thank you.